We're going to look at tutorial number 9, and it's a pretty quick tutorial. There's not a whole lot in there, so this shouldn't take a whole lot of time. In the tutorial, uh, it's assumed that we understand the concept of parallax, and that was introduced in an earlier tutorial that we didn't do. Um, and we have a lot of tutorials dealing with optics, but we only have time this semester to do 3 of those. And so we didn't do the one that included parallax. Um, Now, the idea of parallax is that if you're trying to figure out um, how far something is away relative to something else, and you can't go there, you can't take out a ruler or a tape measure and measure the distance to both of them. Um, how do you do it? Well, astronomers came up with this problem because they weren't sure, which of those spots of light in the sky were further away. And so they came up with this concept of parallax. And parallax is basically this. If I have two objects that are at the same location, when I move my head left and right, they move together because they're both at the same place. But if one of those objects is further away from me, then when I move my head to the left, the object that's further away, in this case the red pen, it's now to the left of the brown pen. And when I move my head to the right, the red pen is to the right of the brown pen. And so we say that the thing that's furthest away moves with your head. Okay. Again, I wasn't watching to see whether that turned out on the recording, but I'll do it again. Um, when I look straight on, um, they're they're right on top of each other, and so I could tell that the brown pen is in front of the red pen because it's blocking some of the red pen. But if I hold it up a little bit so that one's not blocking the other, now I can't tell which one's closer to me, except I know how far my arms are extended. So when you're at home, what you should do is have your spouse or significant other or just a friend um, hold them for you so that you can't just tell by feel. And then when you pull your head to the left, the one that's furthest away is going to move to the left relative to the other one. And when you move your head to the right, the one that's furthest away is going to move to the right relative to the other one. Let me see if I can motivate that on paper. Let's share the screen. Um, if that's the red pen and that's the brown pen, you see that when I'm looking straight on, um, they're in line with each other. And if I have one higher than the other, I really can't tell which one's closer. But if I move my head to the left, now the light that comes from the red pen is going to come in a direction that's to the left of the light that comes from the brown pen. And when I move my head over here to the right, the light that comes from uh, the red pen is coming from a direction that's to the right of the light coming from the brown pen. And so I can tell that they are not at the same distance from my eye and that the red pen is further away from my eye. Now, when astronomers are using this principle, they don't wiggle their head back and forth. What they do is they um, look at two objects. Um, this would be the sun. Of course, the Earth makes its journey around the sun coincidentally in the same amount of time that it takes you to go from birthday to birthday. Isn't that neat? And so if we've got two objects way the heck and gone, and I, can't draw this to scale obviously because they didn't give me enough paper. Um, but you can see that uh, if we just wait 6 months, uh, it's like moving your head from side to side, and you can, if you see a different ordering left to right when it when the Earth is here versus when it's here, it will tell you which of those is further away. Okay, so that is parallax. Parallax. Okie dokie. Now, this tutorial uh, asks that we take a square container of water and mount a pin in it so that half of the pin is below the water and half of the pin is above the water. And we want to put our eyeball down here. We're looking for the part of the pin that's in the water. And we want to see um, what that looks like. We know that light travels slower in water than it does in air, and that because of that uh, change in velocity, that light is going to bend when it gets to the interface between the water and the air. Now, it turns out the water never touches the air on the sides because there's glass there. But the glass is thin, and what we're going to find a little bit later on, we'll do an experiment to prove this, but the glass can be ignored if it's thin enough, and that the real bending happens due to the change in velocity from the water to the air. So it says here, for simplicity in answering the following questions, ignore the walls of the container and use the approximation that light passes directly from the water to the air where it travels more quickly. So now the pin is here. It's in the water towards the back of this square uh, container of water. And I'm just going to pick uh, two rays at random. And we know that when light travels from a slow medium to a fast medium, it bends away from the normal. Well, that means we're going to need some normals here. And you're saying to yourself, I haven't seen many normals around the physics department. Where are you going to find normals? Okay, that's enough physicist jokes, okay? No more physics jokes. Okay, normal just means perpendicular. Doesn't mean you're socially okay. Okay. Now, away from the normal would be like this and like this. Okay. Now, because that bends away from the normal, our brain follows those rays back and convinces itself that they're coming from a different location than where the pin actually is. If I follow this ray back and I follow this ray back, it looks like that pin is right there, and that the rays coming to our eyes um, are coming from that location that we call the image location. And uh, this is a real pin. This is something that I could stick myself with and I would bleed. And so this we call the object. And and geometrical optics is all about, you know, putting an object in front of a curved mirror, a lens, a bunch of water, and finding out where the image is. Where does it look like the light is coming from? Um, so, on the basis of the rays that you have drawn, predict where the bottom of the pin would appear to be located, and that's going to be right there. That's what we found. Okay, there it is. Um, would the bottom of the pin appear to be located closer, further away, or the same distance from the observer as the top of the pin? Well, according to what we know about refraction, it's going to appear uh, closer because light bends away from the normal when you go from slow water to fast air. And then the water's not slow and the air's not fast. It's the light travels slow in the water and fast in the air. So we're going to video that using parallax to check our predictions and make sure that we got the right prediction. And we'll do that and splice that in. We talked about the method of parallax, and with that method, you can determine when two things are the same distance away from your eye by looking at both of them and moving your head back and forth. If those two objects are the same distance from your eye, they'll appear to move together. But if one of them is closer to you and one is further away, when you move your head back and forth, the one that's further away is going to move the same direction as your head. We talked about that earlier. And so when I move my head to the right, the red pen looks like it's going to the right of my finger. When I move my head to the left, the red pen looks like it's going to the left of the finger. And so I just move the red pen until they're moving together. Well, what we're trying to find is the location of the image of this pencil. And you see the image down here in the water, okay? That's not the pencil down there that you're seeing. That's the image of the pencil. And it's in a different location than the pencil itself. And we're going to use this red pen to try to figure out where that location is. Now I'm going to start by putting this red pen about 5 inches in front of the real pencil. And if we could see a top view to just see how far that is away. Okay. And now we're going to move the camera to the left and to the right. And when you move it to the left, you see that the image, that's what's down in the water, moves to the left of the red pen. When we move the camera to the right, the image, again, what's in the water, moves to the right of the red pen. And that tells me that the image is further away from our eyeball, the camera, than the red pen. Well, now if I move that red pen about 1 inch in front of the real pencil, about there, now when we move the camera to the left, They should move together. The image, which is down in the water, and the red pen on top, should move together when the camera moves to the right. They move together, and that means I found the correct location of that image. Okay. So I'm just going to move on here. The place where the pin appears to be located is called the location of the image of the pin, or the image location. In part one, you assume that light from the pin passes directly from water to air. Devise an experiment that would allow you to test whether this approximation is valid. So what we're going to do is we're just going to, first of all, video the pin in the water, and then we're just going to dump the water out of that container and look at it again and see uh, if the if the if the location of the image is still closer to us than the actual pin. And what we're going to find out is that um, with the thin walls of the container, it's really not going to be important. Okay, let's turn the page over. Well, we're going to do the same thing over again, only two changes. First of all, instead of a pen, we're going to use a pencil. And for reasons that we will find apparent. Um, and then we're going to fill this circular beaker with water so that we can see the top part of the pencil out of the water, but we have to look in the water through the glass to see the bottom of the pencil. And so this time when we draw a ray diagram, um, again, we're going to start with the pencil uh, location, and we're going to just draw a couple of rays, random. Okay, I'm just going to draw a couple of rays. Now, the big difference between this setup and the last setup is, of course, the shape of the container. And why that's important is because um, we're bending the light away from the normal, but the normal is perpendicular to the surface. And for a circular surface, I have to make a line that's radially out from the center of the circle. So that would be my normal there. And over here, I would make a radial normal. Okay. So now you might be tempted to make it go away from the normal. Uh, just take a moment and think about why that would be sick and wrong to make it go like that. Sick and wrong. I hope what you said to your brain was, oh no, it always goes to the other side of the normal. It just bends away from the normal a bit. Okay, so it would bend away from the normal and away from the normal. Now, what I have done is if I follow these rays back, I may have made my angles just too extreme so that I'm going to run out of paper here. Okay, these are going to meet somewhere back here. Okay. Now let me repent of those pictures, and just in case I did it beforehand, uh, so that it was a little bit better. What I did was made the bend a little bit more realistic, to what the angles would actually be. And you see that when I uh, have these rays coming out, these are the real light rays that come from the pencil and then bend coming out to where my eye is, but they appear to be coming back from here. Okay. Now, again, we're going to use a different camera here to use the method of parallax again, uh, to place a second pencil at the location of the image and see if we uh, did the right diagram. Okay, now we've got a different situation. This container of water is circular, and we've placed a pencil near the back of the water, and we're going to use again the method of parallax to try to find the location of the image, where the bottom of the pencil appears to be located. Now I'm going to start by just taking a stab in the dark and saying, well, last time we found that the image was in front of the real pencil, so I'm going to try putting my red pen right here, and if we could see a top view to see where that is. Okay. And now we're going to move the camera left and right, and what we're going to find, if you concentrate on the image that's below the water and the red pen that's above the water, you'll see that when the camera goes to the left, the image goes to the left relative to the red pen. And when the camera goes to the right, the image goes to the right relative to the red pen. Now you'll also notice that the image of that pencil is fat, okay? It's wide. And you know, that kind of suggests that, well, maybe that image is closer than the real pen, because when things get closer, they get bigger. But when we looked for it closer, we didn't find it there. So let's try behind the pencil. If I put it clear back here, let's do a top view to see where I am. Well, now when we move the camera, again, let's concentrate on the pencil in the water and the red pen above the water. And what we find now is that the red pen is moving with the camera. When the camera moves to the right, the red pen moves to the right of the image, the part in the water, and when it moves to the left, the red pen moves to the left of the image in the water. So that tells me that the red pen is further away from the camera than the image. So I'm going to put the red pen now in the image location that I found before we turned the camera on. And if we could get a top view of that, please. Okay, so now when we move the camera, concentrate on the image in the water and the red pen above the water, and what you should see is that they move together. They don't change position as the camera moves back and forth. Now I'm having a hard time holding the red pen steady because I'm an old man, but I hope that's what you're seeing in the camera. Okay. So three students are discussing their results from part B, and student one says, I think that the image is closer to me than the pencil itself. The closer something is, the bigger it looks. Because the image of the pencil appears wider than the pencil itself, the image must be closer to me than the pencil. Indeed, what we're going to find with that other camera, or what we did because I spliced it in, what we found when we looked in the water was that the image that we saw through the water of the pencil was wider than the actual pencil. It was fatter. Okay. And so student one saying, oh, things get fatter when they get closer. And so that pencil must have been closer. Student two says, well, that sounds reasonable. I mean, that's the way things work in a lot of cases. But when I used parallax to determine the location of the image of the pencil, I found that it was further from me than the pencil. And that's what we found when we did parallax. So student two is right. Student three says, well, that doesn't make sense. If the image were behind the pencil, then how could I see the image? Wouldn't the pencil block my view of the image? Well, it turns out that the pencil can't block the light from that image because no light is coming from that image. That's not a real thing back there. This image is where the light appears to be coming from. It appears to be sending out rays from that direction, but there's no rays. This line is not actually a ray of light. These rays that are solid are rays of light, but this dashed line is just where the rays appear to be coming from. And so student three um, is missing the point of an image. Okay. Now, if we go to this second page, um, we find that if we place a pin just outside of the circular container of water, that because of these bends, both here and here, the light that gets to our eye appears to be coming from a place back here. Okay. I'm going to move this so I don't see very good anymore. We'll talk about eyesight a little later in class. Okay. So the image would be here. Now, in this case, the rays of light that leave that pin and bend, again, we've got to bend light at each normal. We bend light at this normal and this normal. And then again, at when it comes out of the water, we have to bend it again at that normal and that normal. Okay. And so you see here, we're bending towards the normal because we're going into the slow water. And here we're bending away from the normal. Um, so here, this would be the angle in air, and this would be the angle in the water, and then here it would be, this would be the angle in the water, and this would be the angle in the air. Okay. Now, the image is where the light appears to be coming from. And your brain just follows those rays back to where they appear to be coming from. And so in this case, the image location would be right here. Now, we're asked to answer some questions here. We want to use the ray diagrams above to answer the following questions. In each case, which is further from the observer? So we'll take case 1 and case 2. Okay. So which is further from the observer? Is it the image or the object? And remember, the pin is the object. So in case 1, which one's further away from the observer? That's the eyeball. Okay. And in this case, it's going to be the image. And in this case, it's going to be the, the thing that's furthest away is going to be the object. Now, in each case, which is further from the observer, the image or the beaker of water? Well, in this case, it's going to be the image, and here it's going to be the beaker. Okay. Now we're going to use that other camera to use again the method of parallax to check our answers for cases 1 and 2. In the tutorial, we followed the rays back to find the image location of a pencil that was just outside the circular container of water. And what we found from that construction was that the image was back here behind the actual pencil. And we were asked to verify that with the method of parallax. And so what we're going to do is predict that that location is back here. If I could get a top view of that. And we're going to check that by putting the red pen at that location and moving the camera back and forth. Again, concentrate on the image, which is below the water level, and the red pen that's above the water level, and see if they move left and right together. And they should. Okay. Okay, let's check that last case in the tutorial where the pencil is quite a ways behind that round container of water. And what we found from the ray diagram was that the image, where all the light seems to come from, was quite a ways in front of the beaker of water. And so we've put the red pen there, and we're going to see with the method of parallax whether that is the right location. So again, what you want to concentrate on is the image in the water and the, let's see if we can move the pen towards, okay, perfect. I want to concentrate on the image in the water and the red pen above the water. And you see they're moving about the same. And it's really hard to get the exact location, but you see that they're moving fairly much the same. Now, If I turn the page over, this is the last page. In each of the previous cases, predict what would be seen on a white paper screen placed at the image location. Imagine that the room has been darkened, but that the pin is illuminated. Um, in either case, does the light from the pin that forms the image pass through the image location? Well, let's go back to our two cases. Uh, when I shine light on that pin, it bounces off the pin in all different directions. But the light that comes to me over here um, isn't light that ever came from the image. Okay. It appears to come from that location, but no light actually came from that image to my eye. On the other hand, in case two, all of the light that left the pin and went through the water got brought back together right here and then spread out again. It kind of went right through each other. And so all of the light appears to come from a location where light actually went and kept going. Okay. So there's actual light here. And so in um, case one, the answer is no. And case two, the answer is yes. So if I were to take a screen and put it over here at the image, um, it wouldn't give me a bright spot, okay? But if I put a white screen right there in a darkened room, I would, and if this were, say, a point source of light, I would get a bright spot on my screen. And if I put a screen here, no spot. Here I would get a bright spot. Now, what we're trying to establish here is the difference between uh, a real image. This would be a real image, and this would be what we call a virtual image. A real image, I can put I can put a screen there and it lights up the screen. Okay. A virtual image is just where the light appears to come from. If I am showing a movie from a projector, um, I want to be able to put up a projector screen and 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 have that part of the screen that has Bambi in the movie show me Bambi. Okay, it's got to light up, and so those at a movie theater would be a real image. We'll talk more about virtual images in class. Um, if we replace the pin with a lighted long filament bulb, we will see that we can actually get a bright spot of light in case two, but not in case one. One of the images in part A is real, the other virtual. Explain how you can tell which image is real and which is virtual on the basis of the ray diagrams and your observations in part B. So from the ray diagrams, I asked, does light actually come from that location to my eye? If so, it's real. If not, it's virtual. And two, can I project it on a screen? If I can, uh, then it's real. If not, it's virtual. Explain how you can use a screen to determine the location of an image. Well, if I didn't have these diagrams here, I could just put something over here and move the screen closer and further away until the light, the image of my object is in focus. When all that light that leaves the pin is brought back together again, it will be a sharp point again, and that would be the image location. Okay. Again, we're going to get another camera and make those observations in the water, and then I'll splice those in, and this will be the end of that tutorial. And I hope you're having a good day.